Everything ends. Every star you can see tonight, every star you cannot see, every galaxy, every planet, every atom of every world that has ever existed or will ever exist is moving slowly and inexorably toward an ending. Not a pause, not a transformation into something new and vibrant. An ending in the fullest and most final sense of the word, a state from which nothing further can happen ever again for the rest of time, and the rest of time is very, very long. This is not a metaphor, and it is not a fear I'm inventing to unsettle you. It is the considered conclusion of modern physics, drawn from the same equations and the same observations that let us build the machines you are watching this on, the same science that put spacecraft on other worlds and gave us the first photographs of black holes. The universe had a beginning, and by every serious line of evidence we possess, it will have an end. And tonight we are going to follow the entire story, from now until the very last event that will ever occur, across a span of time so enormous that the current age of the universe, 13.8 billion years, will come to seem, by the time we are finished, like the first fraction of the first second of a life that lasts an eternity. We are going to watch the stars go out, one by one, over trillions of years. We are going to watch the galaxies drift apart and vanish from one another's skies. We are going to watch matter itself begin to decay, atoms unraveling, everything that was ever solid dissolving into a thin cold mist of particles. We are going to watch the black holes, those last and most enduring monuments of the cosmos, slowly evaporate over spans of time that make everything before them look instantaneous. And we are going to arrive, at last, at the final state of the universe, the condition physicists call the heat death, a darkness so complete, a cold so absolute, a silence so total, that the very concept of time begins to lose its meaning, because nothing will ever change again. This is the true story of how everything ends, and it is stranger and in a way more beautiful than any ending ever imagined. Before we begin the long descent into the far future, 3 quick things. If you are new to this channel, subscribe, because this is what we do here. Long, slow, deeply researched journeys through the universe and its deepest questions. The kind of thing you can put on at night, close your eyes, and let carry you somewhere vast and quiet. Hit the like button, because it genuinely tells the platform to show this to other people who think about these things in the dark. And leave a comment telling me where in the world you are watching from and what time it is there. Because I read every single one, and there is something I love about knowing that this meditation on the end of everything is playing right now, in a bedroom in Tokyo, a kitchen in Buenos Aires, a parked car in Ohio at 3 a.m. Wherever you are, whatever hour it is, stay with me all the way to the end, because the end in this case is quite literally the point, and the final minutes of this journey contain ideas that may change the way you think about time, about existence, and about the strange privilege of being alive at the very beginning of a universe that has almost all of its history still ahead of it. Now settle in. Let us begin not at the end, but here in the present, in the universe as it is tonight, so that we understand exactly what it is that is going to be lost and why. Because to appreciate an ending, you first have to understand what was there to end. And the universe we live in right now, this brief and brilliant era, is in many ways the golden age of the cosmos, a time of light and warmth and structure that will never come again once it has passed. We live in an age of stars. Look up on a clear night and you see them scattered across the dark, and it feels permanent, eternal, as though the stars have always been there and always will be. But the age of stars is a phase, a chapter, and by the standards of the full lifespan of the universe, it is a remarkably brief one. Stars are born, they burn, and they die, and the raw material from which they are made, the hydrogen gas that fills the galaxies, is finite. Every star that ignites consumes some of that fuel and locks part of it away, and there will come a time, distant but certain, when the last of the star-forming gas has been used up, when no new stars can form, and the existing stars begin, one after another, to go dark. We are living in the era when the lights are on, but the lights are being switched off slowly across timescales beyond human comprehension, and they will not be switched back on. To understand where the universe is going, we have to understand the force that is driving it there, the great engine of cosmic change. And that engine has a name. And it is one of the most important and most unsettling discoveries in the history of science. The engine is the expansion of the universe and its acceleration. And to understand the end of everything, we must first understand this. In the 1920s, the astronomer Edwin Hubble, working with one of the great telescopes of his day, made a discovery that shattered the prevailing picture of a static, eternal, unchanging cosmos. He found that the galaxies beyond our own are not sitting still. They are moving away from us, and more than that, the farther away a galaxy is, the faster it is receding. This was the first observational evidence that the universe is expanding, that space itself is stretching, carrying the galaxies apart from one another, like raisins in a rising loaf of bread, every point moving away from every other point as the dough swells. This single discovery transformed our understanding of everything. If the universe is expanding now, then in the past it was smaller, denser, hotter, and if you run the film backward far enough, you arrive at a moment when everything we can see was compressed into an unimaginably hot and dense state. The beginning we call the Big Bang, some 13.8 billion years ago. But the discovery of expansion did more than reveal our origin. It raised immediately and unavoidably the question of our destiny, because the future of the universe depends entirely on what the expansion does over the vast reaches of time to come. For most of the 20th century, cosmologists believed that there were essentially three possible fates for the universe, three roads it might travel, and which road we were on depended on a single question: whether there was enough matter in the universe for gravity to eventually halt and reverse the expansion. The first possibility was that the universe contained so much matter that the collective gravity of everything would eventually overcome the expansion, slow it, stop it, and then pull everything back together. The galaxies rushing toward one another once more, faster and faster, until the entire cosmos collapsed back into a hot, dense point, a mirror image of the Big Bang, an ending sometimes called the Big Crunch. In this scenario, the universe would end not in cold and darkness, but in fire. Everything crushed back together in a final cataclysm. And some speculated that such a crunch might even bounce, might trigger a new Big Bang, a new universe rising from the ashes of the old, an eternal cycle of birth and death and rebirth. The second possibility was that the universe contained exactly the right amount of matter, balanced on a knife's edge, so that the expansion would slow down forever, approaching a halt, but never quite stopping, never reversing, coasting outward for eternity at an ever-decreasing rate. And the third possibility was that the universe did not contain enough matter to halt the expansion, so that it would simply continue expanding forever, the galaxies drifting apart without end, growing ever more distant, ever more isolated in a cosmos that grew colder and emptier as it swelled. For decades, the great project of observational cosmology was to measure the universe precisely enough to determine which of these three fates awaited us, to weigh the cosmos and discover whether there was enough matter to bring about the fiery crunch, or the eternal coast, or the endless cold expansion. And then in 1998, two competing teams of astronomers, working independently and racing each other to the answer, made a discovery so unexpected that at first they did not believe their own results. A discovery that would earn them the Nobel Prize and would reveal that the universe is far stranger and its fate far darker than any of the three classic scenarios had supposed. They were studying distant supernovae, exploding stars of a particular type that always shine with very nearly the same intrinsic brightness, which makes them enormously useful as cosmic mileposts. Because by comparing how bright such a supernova appears to how bright we know it truly is, we can calculate precisely how far away it is. And by measuring both the distances and the recession speeds of supernovae across billions of light years, the astronomers hoped to measure how much the expansion of the universe had been slowing down over cosmic history, because everyone assumed it must be slowing, that gravity must be gradually applying the brakes to the cosmic expansion, the only question being how hard. What they found instead was the opposite. The expansion of the universe is not slowing down. It is speeding up. Over the last several billion years, the galaxies have been flying apart from one another, not more slowly but more quickly, as though some mysterious force were pushing them, accelerating the expansion, overwhelming the gravity that should be holding everything back. This was one of the most shocking discoveries in the history of science because it revealed the presence of something no one had predicted, a force that pervades all of space, a repulsive pressure that grows more dominant as the universe expands, and which is driving the cosmos apart at an ever-increasing rate. Physicists gave this mysterious force a name, though the name is really just a label for our ignorance. They called it dark energy, and to this day we do not know what it is. We know it is there because we can measure its effects with great precision. We know it makes up the majority of the total energy content of the universe, far more than all the matter, all the stars and galaxies and gas and dust combined. And we know that it is the single most important factor in determining the fate of the cosmos. Because it is dark energy, this strange and invisible pressure woven into the fabric of empty space itself, that is driving the universe toward its ending and shaping the character of that ending and determining which of the possible endings will actually come to pass. The discovery of dark energy essentially eliminated the big crunch from serious consideration, at least as things currently stand, because a universe whose expansion is accelerating is not going to slow down, stop, and collapse. It is going to expand forever, faster and faster, and that acceleration changes everything about the far future and about the nature of the end. To tell the story of the end of the universe properly, we need a map of time, and the map that cosmologists use divides the entire history and future of the cosmos into a series of vast eras, each one defined by the dominant processes and structures of its age, each one longer than the last, stretching forward into a future so deep that the numbers involved cease to have any intuitive meaning at all. We are going to travel through these eras one by one, from the age we live in now all the way to the final darkness. And I want to prepare you for the scale of what is coming, because the timescales are going to grow so enormous, so quickly, that ordinary ways of writing and thinking about numbers will break down entirely. We will soon be dealing with spans of time written not as ordinary numbers, but as 10 raised to enormous powers, and even those will eventually fail us. But we begin in familiar territory, in the era we ourselves inhabit, the age of stars, which cosmologists call the stelliferous era, from the Latin for star-bearing. This is the era in which the universe is filled with shining stars, gathered into galaxies, illuminating the darkness, forging the heavy elements, warming the worlds that orbit them, providing the energy that, on at least one world, and perhaps many, has given rise to life. The stelliferous era began a few 100 million years after the Big Bang, when the first stars ignited in the cooling darkness. And we are living right now, roughly 13.5 billion years into it. It feels like a long time, and by human standards, it is unimaginably long. But the stelliferous era is not close to over. It will continue, by most estimates, for something like 100 trillion years, which means that if we measure the age of stars from its beginning to its end, we are currently living in only the first 10,000th of it, the equivalent, if the whole era were a single human life of 80 years, of the first few hours after birth. The age of stars has barely begun, and yet it, too, will end, because the process that sustains it is finite. Stars form from clouds of gas, primarily hydrogen, collapsing under their own gravity, until their cores become hot and dense enough to ignite nuclear fusion. But the supply of star-forming gas is limited, and every generation of stars consumes some of it and locks part of it away in stellar corpses that will never return it to circulation. Over the vast span of the stelliferous era, galaxy by galaxy, the gas is gradually used up, and the rate of new star formation, which was tremendous in the early universe, declines and declines, until eventually there is not enough gas left to form new stars at all. And here we encounter one of the first great asymmetries of cosmic time, one of the first hints of how the character of the universe will change. Not all stars are alike, and crucially, they do not live for the same length of time. The most massive stars, the brilliant blue giants that blaze with the light of hundreds of thousands of suns, burn through their fuel with reckless speed and die young, in just a few million years, ending their lives in the tremendous explosions we call supernovae. Stars like our own sun of middling mass live for billions of years, burning steadily and moderately, before swelling into red giants and then fading into white dwarfs. But the smallest stars, the dim red dwarfs that make up the overwhelming majority of all the stars in the universe, live almost inconceivably long. A red dwarf burns its fuel so slowly, so frugally, so patiently, that it can continue shining not for millions or billions, but for trillions of years, 10 trillion, 20 trillion, some of them potentially far longer, dwarfing the entire history of the universe up to this point by a factor of 1,000 or more. And so the end of the stelliferous era is not a sudden thing. It is a long, slow fading, in which the bright, massive stars die first, and then the sun-like stars. And finally, over the immense stretches of deep time, even the long-lived red dwarfs begin, one by one, to exhaust their fuel and go dark. The galaxies dim gradually, the blaze of the early universe giving way to a duller and redder glow, as the population of stars shifts toward the faint and the long-lived until at last, roughly 100 trillion years from now, the final red dwarf flickers out. The last star in the universe dies, and the age of stars, which had seemed so permanent to the brief creatures who lived in its dawn, comes quietly to an end. And here I want you to pause and feel the weight of that image, because it is one of the most profound in all of cosmology. There will come a moment, a specific if unmarkable moment, when the last star in the entire universe burns out. Not a star in our galaxy, not a star in our region, but the last star anywhere, the final source of natural starlight in the whole of the cosmos, guttering out like a candle at the end of a long night. And after that moment, the universe enters a darkness from which it will never emerge. A darkness that will deepen and lengthen for spans of time that make the entire preceding history of the cosmos, all the billions of years of stars and galaxies and life, seem like a single bright flash at the very beginning of an endless dark. But before we follow the dying of the stars all the way to that final darkness, we need to return to dark energy, because its accelerating push is doing something to the large-scale structure of the universe that is, in its own way, as profound as death of the stars, and far more imminent. And it will reshape the very sky that any future observers might look up into. Right now, when we look out into the universe, we see it teeming with galaxies. Our telescopes, pointed at even the smallest patch of apparently empty sky, reveal thousands upon thousands of galaxies, stretching back across billions of light years and billions of years of cosmic history, an overwhelming abundance of island universes scattered across the dark. This is one of the great glories of our present cosmic era, that the universe is observable, that its history is written in the light reaching us from countless distant galaxies, that a curious species arising on a small world can look out and see the vast structure of the cosmos laid out before it, and from that view reconstruct the entire story of where everything came from. But this observability is temporary. It is a feature of the particular era we happen to live in, and dark energy is going to take it away. Because as the expansion of the universe accelerates, the galaxies that are not gravitationally bound to us are receding from us faster and faster, and the space between us and them is stretching more and more rapidly, and there will come a time when they are receding so fast, carried away by the expansion of space itself, that their light can no longer reach us at all. When the space between us and a distant galaxy is expanding faster than the speed of light, and space itself can expand faster than light, even though nothing can move through space faster than light, then the light from that galaxy can never cross the ever-widening gulf to reach our telescopes, and that galaxy effectively vanishes from our observable universe, disappearing beyond a horizon of visibility, gone forever, as though it had never existed. And this is happening right now, all the time, to galaxy after galaxy. The observable universe is not growing in the way you might expect. In terms of the actual objects we can see, it is shrinking as more and more galaxies cross that horizon and disappear from view, carried beyond our reach by the accelerating expansion. Over the coming billions of years, one by one, the distant galaxies will redshift into invisibility, their light stretch to longer and longer wavelengths until it fades below detectability, and then they will be gone. Now, our own galaxy, the Milky Way, is part of a small, gravitationally bound group of galaxies called the Local Group, dominated by ourselves and the great Andromeda Galaxy. And these galaxies are held together by their mutual gravity strongly enough to resist the cosmic expansion. In fact, as we have explored in another journey, The Milky Way and Andromeda are actually moving toward each other and will eventually collide and merge, and the galaxies of the local group will, over the coming tens of billions of years, gradually merge into a single vast elliptical galaxy. So we will not lose our immediate neighbors. But everything beyond the local group, all the other galaxies, all the other galaxy clusters, all the grand structure of the cosmos stretching across billions of light years, all of it is receding, and all of it will eventually vanish beyond the horizon of visibility. And here is a thought that I find genuinely haunting, one of the most poignant implications in all of cosmology. Imagine a civilization that arises in the far future, hundreds of billions of years from now, long after all the external galaxies have vanished beyond the horizon. On some world orbiting some long-lived star in the merged remnant of our local group, such a civilization, looking out into the cosmos with the finest telescopes they could build, would see nothing beyond their own galaxy. The rest of the universe would be gone, invisible, receded beyond all possibility of detection. They would see their own island of stars, surrounded by an infinite and apparently empty blackness. And they would have no way of knowing from observation alone that the universe had ever been anything other than this. No way of discovering the expansion. No way of finding the evidence of the Big Bang. No way of reconstructing the true history and structure of the cosmos. The very evidence that allowed us to understand our universe, the light of distant galaxies, the observable expansion, the afterglow of the Big Bang, will have faded away, erased by the accelerating expansion, and any future astronomers would be left with a profoundly incomplete and misleading picture, convinced perhaps that their single galaxy floating in an eternal void was the totality of existence. We are, in this sense, living in a privileged moment for cosmology, a window of time in which the universe is still young enough that its history remains legible, written in the light of the galaxies we can still see. That window is closing. The knowledge is quite literally fading from the sky. And 100 billion years from now, the truth about the universe will have become, for anyone living then, unknowable, receded beyond the horizon along with the galaxies that carried it. We happen to be alive at the one time when the whole story can still be read, and that is a kind of cosmic luck so extraordinary that it is worth pausing to marvel at it. We arrived early enough to see. Before we let the story rush ahead into the truly deep future, let us linger for a while in the nearer reaches of cosmic time, in the next few billions and tens of billions and hundreds of billions of years. Because even these relatively near-term stretches of the future contain events of extraordinary drama and beauty, and they are, in a sense, more real to us, more connected to our own world and our own galaxy than the abstract eras of the deepest future. In about 1 billion years, as we have discussed, the slowly brightening sun will render the Earth uninhabitable, boiling away its oceans, ending the long story of life on our world, unless that life has found a way to spread elsewhere. In about 5 billion years, the sun will swell into a red giant and then collapse into a white dwarf. And our solar system as we know it will end. But the galaxy around us will continue, and it too has its own dramatic future. In about 4 to 5 billion years, our Milky Way galaxy will collide with the great Andromeda galaxy, our nearest large galactic neighbor, currently rushing toward us across the intergalactic void at 110 kilometers per second. This collision, which we have explored in detail in another journey, will not be a violent smashing of worlds, because the stars within galaxies are so far apart that almost none of them will actually collide. Instead, the two galaxies will pass through each other, their gravitational fields distorting both into streaming ribbons of stars, triggering bursts of new star formation, and then, over hundreds of millions of years, they will fall back together and merge, eventually settling into a single vast elliptical galaxy that astronomers have nicknamed Milkomeda. Our sun, or the white dwarf it will have become, may be flung into a new orbit within this merged galaxy, perhaps toward its outskirts, perhaps toward its center, but will most likely survive the merger intact, one star among the hundreds of billions rearranged by the great galactic collision. And this merger is just the beginning of the gathering together of our local cosmic neighborhood. The local group, the small cluster of galaxies to which the Milky Way and Andromeda belong, is gravitationally bound, held together against the cosmic expansion, and over tens of billions of years, All the galaxies of the local group will gradually merge into a single enormous galaxy, a final island of stars that will persist, isolated in the deepening void. Meanwhile, beyond the local group, the accelerating expansion will be carrying all the other galaxies away, and over the next 100 billion years or so, they will recede beyond the horizon of visibility, one by one, until our merged galaxy is alone, surrounded by an apparently infinite and empty blackness. So picture the universe 100 billion years from now. Our galaxy, the merged remnant of the entire local group, floats alone in the void, its stars still shining, though the brightest and most massive are long dead, and the galaxy glows more redly than it does today. Beyond it, nothing, only the empty dark, all the other galaxies gone, receded beyond reach, invisible and unreachable, their light forever unable to cross the ever-widening gulf. Any beings alive in that galaxy would see a cosmos utterly different from ours, a single island of stars in an endless void, with no way of knowing that the universe had ever contained anything more. This is a strange and lonely future, but it is still, in a sense, a living future, a future of stars and light and the possibility of life. And it will persist for a very long time, because the long-lived red dwarf stars will continue shining for trillions of years, keeping the isolated galaxy lit, if dimly, deep into the future. And it is worth pausing to appreciate the strangeness of this isolation, the way the accelerating expansion is, in effect, carving the universe up into ever more isolated islands, each one cut off from all the others, each one an entire cosmos unto itself, unable to see or reach or communicate with anything beyond its own boundaries. The grand connected cosmos of our own era, in which we can see billions of galaxies stretching across billions of light years, is a temporary condition, a feature of the youth of the universe, and it is giving way, slowly but inexorably, to a future of isolation, of separation, of each surviving island of stars alone in its own private darkness, forever severed from all the rest. We live in the connected age, the age when the universe is still small enough and young enough that its parts can still see one another, still influence one another, still form a single comprehensible whole. And that age, like all the others, is passing, giving way to the long isolation of the deep future, in which the pieces of the cosmos drift apart forever, each one alone. And through all of this, the merged galaxy shining alone in its void, the red dwarfs burning slowly down, the isolation deepening, the great cosmic clock ticks steadily onward, carrying the universe from its bright and connected youth toward its dark and isolated and eventually lifeless old age, one era giving way to the next in the long, slow procession toward the final darkness. Let us now cross the great threshold, the death of the last star, and enter the era that follows, the first of the truly deep future ages, the one cosmologists call the Degenerate era. The name comes from the strange forms of matter that dominate this age, the degenerate remnants left behind when stars die, and it is an era that will last vastly longer than the age of stars that preceded it, stretching from roughly 100 trillion years after the Big Bang to something like 10 duodecillion years, a span so long that the entire stelliferous era, all 100 trillion years of it, is less than a rounding error by comparison. When a star dies, it does not simply vanish. It leaves behind a corpse, and the nature of that corpse depends on the mass of the star that died. The smallest stars, the red dwarfs, will eventually become white dwarfs, dense cinders of degenerate matter roughly the size of the Earth, but containing a substantial fraction of the mass of the Sun, so dense that a single spoonful would weigh many tons. Stars like our Sun also end as white dwarfs after passing through a red giant phase and shedding their outer layers. And the most massive stars and the ones that die in supernovae leave behind either neutron stars, even denser objects in which the matter has been crushed until the very atoms have collapsed and the star has become essentially a single vast atomic nucleus a few kilometers across, or for the most massive stars of all, black holes, regions where the collapse has gone all the way, where gravity has become so extreme that not even light can escape. So as the stelliferous era ends and the degenerate era begins, the universe is populated not by shining stars but by their corpses, A vast and growing population of white dwarfs and neutron stars and black holes, scattered through the fading galaxies, cooling slowly in the deepening dark. The white dwarfs, when they first form, are extremely hot, glowing white with residual heat, which is why they are called white dwarfs. But they generate no new energy. No fusion sustains them, and so they do nothing but cool, slowly radiating away their heat into the cold of space, growing dimmer and redder over billions and then trillions of years, fading from white to yellow to red, to a dull infrared glow, and finally, after immense spans of time, cooling all the way down to become what are sometimes called black dwarfs, cold, dark cinders no longer emitting any appreciable light at all, invisible corpses drifting through the dead galaxies. It is worth noting that not a single black dwarf exists in the universe yet. Not one, because the universe is not yet old enough for even the oldest white dwarfs to have cooled all the way down. The formation of the first black dwarf lies far in the future, and it is one of the milestones that marks the deepening of the Degenerate era. So picture the universe of this age. The galaxies still exist, or rather, the merged remnants of galaxies exist, but they no longer shine with the light of living stars. Instead, they are filled with the cooling corpses of stars, white dwarfs slowly fading, neutron stars spinning down, black holes lurking in the dark, all of it growing colder and dimmer and more silent as the eons pass. There is still some faint light in this era, but it is a pale and dying thing. The occasional flicker comes from rare events, the collision of two stellar remnants perhaps, or a burst of activity as some object falls into a black hole. Brief flares in an ever-deepening darkness, and there is one source of new starlight, faint and sporadic, that persists even into this dark age, and it is a strange and lovely one. Occasionally, two brown dwarfs, objects that were never quite massive enough to ignite as true stars, failed stars drifting cold and dark through the galaxy, will happen to collide and merge, and if their combined mass is enough, the merger can ignite fusion, creating a new, small, dim star that will shine for a while before it too burns out. Across the vast reaches of the Degenerate era, these rare collisions will occasionally spark a brief new star into being, a tiny flame flickering to life in the encompassing dark, burning for a few billion years, and then dying. And at any given moment in this era, a galaxy might contain a mere handful of such stars, or none at all, scattered points of light in a darkness that was once ablaze with hundreds of billions of suns. The contrast is almost unbearable to contemplate. The galaxies that once blazed with the combined light of hundreds of billions of stars, that lit up the cosmos and warmed countless worlds, reduced to dark reliquaries of stellar corpses, illuminated only by the rare and lonely flicker of a chance collision. The vast majority of their light long since extinguished, the age of brilliance a distant memory, encoded only in the cooling embers of the dead. And yet, even this is not the end. The Degenerate era, for all its darkness, still contains matter, still contains structure, still contains the ordered remnants of the age of stars. There is still, in a sense, something there. But the deep processes of physics are not finished with the universe. And in the Degenerate era, a new and even more fundamental kind of decay begins to make itself felt. A decay that will attack not just the stars, but the very building blocks of matter itself. And it is to this that we now turn, because it is one of the strangest and most uncertain chapters in the whole story of the end. Everything you have ever touched, everything you have ever seen, your own body, the ground beneath you, the air you breathe, the stars in the sky, is built from atoms, and atoms are built from a small number of fundamental particles, protons and neutrons, clustered in the nucleus, electrons orbiting around them. These particles have always seemed, to our intuition and to much of our physics, to be permanent, eternal, the stable and unchanging bedrock of reality. A proton in particular has long been considered essentially immortal, a particle that, once formed in the early universe, would persist unchanged forever. But some of our theories of fundamental physics suggest that this may not be true, that even the proton, that most stable and enduring of particles, may itself be subject to decay, may itself, given enough time, unravel into simpler components and cease to exist. If protons do decay, and it is important to say clearly that this has never been observed and remains uncertain, then the timescale for that decay is staggeringly long, on the order of 10 to the 34th years or vastly longer, a number so enormous that a proton is, for all practical purposes on any timescale we normally consider stable. But the degenerate era lasts far longer even than that, and over its immense span, if proton decay is real, then the protons that make up all the matter in the universe will, one by one, begin to decay, and this will spell the end of matter as we know it. Imagine a white dwarf, a black dwarf by now, a cold, dark cinder that was once a star, drifting through a dead galaxy. It is made of ordinary matter, of atoms, of protons and neutrons and electrons. And slowly, over unimaginable spans of time, its protons begin to decay. One here, one there, each decay releasing a tiny bit of energy and radiation. Each decay removing one more brick from the structure of the object. Over enough time, as more and more of its protons decay, the black dwarf slowly evaporates, slowly dissolves, its matter converting into radiation and lighter particles, until eventually, after a span of time so long that it dwarfs everything that came before, the black dwarf is gone entirely, dissolved into a thin haze of particles drifting apart in the dark. And this happens not just to one black dwarf, but to all of them, to every white dwarf and black dwarf, to every neutron star, to every scrap of ordinary matter in the universe. Over the reaches of the degenerate era, if proton decay is real, all the ordinary matter in the cosmos, all the stellar corpses, all the planets, all the cold dead worlds, everything built from atoms, slowly evaporates away, dissolving particle by particle into radiation, and the lightest, most stable debris, until the universe is emptied of atoms altogether, emptied of everything that was ever solid, everything that was ever a world, or a star, or a body. Consider what this means. Somewhere in the deep future, the last atom in the universe decays. The last proton, the last remnant of all the ordinary matter that ever existed, that once formed stars and planets and living things, that once made up your own body, unravels and is gone. And after that moment, there is no ordinary matter anywhere in the cosmos. None at all. Forever. Everything that was ever solid, everything you could ever have held in your hand, will have dissolved into a thin, cold, ever-expanding mist of fundamental particles, drifting apart in an ever-darkening void. And even as the matter within them decays, the galaxies themselves, or their dark remnants, are also coming apart in another way through a slow gravitational unraveling. Over immense timescales, the stellar remnants within a galaxy interact gravitationally, and through these interactions, some remnants are flung outward and escape the galaxy entirely, while others lose energy and spiral inward toward the massive black hole at the galaxy's center. Slowly, over spans of time on the order of 10 to the 19th or 10 to the 20th years, the galaxies dissolve, some of their contents scattered into intergalactic space, some swallowed by the central black holes, until the ordered structure of the galaxy, which had persisted in some form since the age of stars, finally comes apart, and the remnants are either isolated and drifting alone in the vast dark, or consumed by the growing black holes at the centers of what were once galaxies. So by the end of the degenerate era, the universe has been transformed almost beyond recognition. The stars are long dead. The stellar corpses have either evaporated through proton decay or been scattered and swallowed. The galaxies have dissolved. The ordinary matter is gone, unraveled into radiation and stray particles. What remains, drifting in the immense and ever-expanding darkness, are the black holes, the last great structures in the universe, the final monuments of the age of matter, and a thin, cold gas of the particles left over from all the decay, and the whole thing expanding, always expanding, growing colder and emptier and more silent with every passing eon. The black holes are all that is left with any substance, any structure, any concentration of mass energy in the encompassing void. And so the universe enters its next great age, the age of the black holes, the black hole era, in which these dark objects, having outlasted everything else, having endured while stars died and matter decayed and galaxies dissolved, reign alone over a cosmos of almost perfect emptiness. But even the black holes, those most enduring of all things, Those objects from which nothing can escape are not truly eternal, and their long, slow doom is one of the most beautiful and strange discoveries in all of physics. For most of the history of physics, black holes were thought to be truly permanent, truly eternal. A black hole is defined by the fact that nothing can escape it, that its gravity is so overwhelming that not even light can climb out of it. And if nothing can ever escape, then it seemed obvious that a black hole could only ever grow, swallowing whatever fell into it, never diminishing, enduring, unchanged forever. And then, in 1974, a young physicist named Stephen Hawking made one of the most surprising and profound discoveries in the history of science. A discovery that combined the physics of the very large, the physics of gravity and black holes, with the physics of the very small, the physics of quantum mechanics, and revealed that black holes are not, after all, eternal. They glow ever so faintly, they radiate, and over unimaginable spans of time, they evaporate and die. The physics behind this is subtle, but the essence of it can be grasped. The empty vacuum of space, according to quantum mechanics, is not truly empty. At the smallest scales, it's seized with activity, with pairs of particles and their antiparticles constantly flickering into existence and then annihilating one another and vanishing again, borrowing energy from the vacuum for the briefest of instants before paying it back. This is a strange but well-established feature of quantum physics, the restless energy of empty space itself. Now near the boundary of a black hole at the edge called the event horizon, something remarkable can happen to these flickering pairs of particles. Occasionally, one member of a pair falls across the event horizon into the black hole, while the other escapes outward into space. The escaping particle carries away energy, real energy, and by the accounting of physics, that energy has to come from somewhere, and it comes from the black hole itself, which loses a tiny bit of its mass in the process. So, the black hole, through this quantum process at its boundary, very slowly radiates energy away and very slowly loses mass, and over time, shrinks. This radiation is called Hawking radiation, and it means that a black hole is not eternal but is, instead, slowly evaporating, leaking its mass away into space one particle at a time, over spans of time that are almost impossible to comprehend. And here we encounter one of the strangest features of black hole physics, which is that smaller black holes are hotter and evaporate faster, while larger black holes are colder and evaporate more slowly, so that the largest black holes take the longest of all to die. A black hole with the mass of our sun would take something like 10 to the 67th years to evaporate completely through Hawking radiation, a number so vast that the entire prior history of the universe, all the trillions of years of stars and the far longer ages of matter decay, is nothing beside it. And the largest black holes, the supermassive black holes at the centers of galaxies, the ones with masses of millions or billions of suns, take vastly longer still, on the order of 10 to the 100th years, or for the very largest, even longer spans of time that require numbers with more than 100 digits to express. So the black hole era is the longest era of all, an age in which the universe consists of almost nothing but black holes, slowly, imperceptibly evaporating, scattered across an unimaginably vast and empty and cold expanse of space, each one radiating its faint Hawking glow into the encompassing dark, each one shrinking by degrees so tiny and over spans so long that the process seems, on any comprehensible timescale, to be no process at all. For most of the black hole era, a black hole evaporates so slowly that it appears utterly static, unchanging, eternal. But it is not. Slowly, over 10 to the 67th years, over 10 to the 80th years, over 10 to the 100th years, the black holes shrink. And here is a strange and beautiful thing about the way a black hole dies. As it evaporates and loses mass, it grows smaller, and as it grows smaller, it grows hotter, and as it grows hotter, it radiates faster, and so the evaporation accelerates. For almost the entire life of a black hole, this acceleration is imperceptibly slow. But in the final moments of a black hole's existence, after all those uncountable years of patient, glacial evaporation, the process runs away with itself. The black hole, now tiny, now blazingly hot, radiates faster and faster, shrinking more and more rapidly, until in a final instant it releases the last of its energy in a burst of radiation, a flash of particles and light, and then it is gone. After 10 to the 100th years, after a span of time that beggars all comprehension, a supermassive black hole that had endured while stars died and matter decayed and galaxies dissolved and the ordinary universe passed entirely away, finally in a last brief flare, evaporates completely and ceases to exist. And one by one across the immense and ever-expanding darkness, the black holes die. The last great structures in the universe wink out, each one ending in its final burst of Hawking radiation, until at last the largest and longest-lived black hole of all, somewhere in the deep and lonely dark, radiates away the last of its mass and vanishes in a final flash. And with it goes the last concentration of mass and energy, the last structure, the last object, the last thing in the entire universe. And after that flash fades, the universe contains no stars, no matter, no black holes, no structure of any kind, nothing but a thin and ever-thinning gas of the particles and radiation left over from all that has decayed and evaporated, drifting apart in an infinite and ever-expanding void, growing colder and colder, approaching but never quite reaching the absolute zero of temperature, in a darkness and a silence and an emptiness that will endure, unchanging, for the rest of eternity. And now let me take you to the very strangest reaches of the deep future, to events so bizarre and so remote that they push at the very limits of what physics can describe. Events that would occur only if proton decay does not happen. Only if protons are truly stable and matter does not simply evaporate away. Because if protons are stable, then the story of the far future becomes even stranger and even longer, extending to timescales that make even 10 to the 100th years seem brief. Timescales that require numbers so large they can barely be written down. Consider what happens to matter if it does not decay. The cold, dead stellar remnants, the black dwarfs and neutron stars, would persist, but they would not remain unchanged, because even solid matter, over sufficiently vast timescales, behaves in strange and counterintuitive ways. Over spans of time on the order of 10 to the 1500th years, a number I can barely even name, ordinary matter would slowly rearrange itself through the bizarre quantum process called tunneling, in which particles pass through barriers they could not classically cross. And through this incredibly slow quantum creep, all matter would gradually transform. The nuclei of atoms would slowly fuse and fission, creeping toward the most stable configuration, which is iron, so that over these unimaginable spans of time, every object in the universe, every cold, dead remnant, would slowly transform into iron, becoming what physicists call an iron star. A cold sphere of pure iron, the ultimate end state of matter, the most stable form into which the elements can settle. Imagine that, in a future so distant that the number of years requires 1,500 digits to write, the cold dark corpses of the stars would have transformed, atom by atom, through the slow magic of quantum tunneling, into spheres of pure iron, drifting frozen and lightless in the eternal dark. The final and most stable form of matter in a universe long since gone cold. And even these iron stars would not last forever. Over timescales even more staggering, on the order of 10 raised to a power that is itself a huge number, the iron stars would themselves collapse. Through the same quantum tunneling, given enough time, an iron star could tunnel into a more compact configuration, could collapse into a neutron star, or even, over spans of time beyond all conception, into a black hole, which would then itself evaporate through Hawking radiation, returning even these ultimate remnants to the thin cold gas of the dying cosmos. These are timescales that have no meaning, no analogy, no possible intuitive grasp, timescales so vast that the distinction between them and infinity becomes almost philosophical, and they describe events that may never actually occur, because they depend on the stability of the proton, which we do not know, and because the accelerating expansion may change the rules long before such events could happen. But they illustrate something profound about the nature of the deep future, which is that nothing is truly permanent, that even the most stable and enduring things, given enough time, transform and decay and pass away, that on a long enough time scale, everything happens, everything changes, Everything ends, and the only true constant is change itself. The relentless working of physics grinding away at even the most enduring structures across spans of time that make the entire history of the universe up to now seem like less than an instant. And there is something almost dizzying, almost vertiginous, in contemplating these ultra-deep timescales, in realizing that the story of the universe extends so far beyond anything we can comprehend, that after the death of the last star, after the decay of matter, after the evaporation of the black holes, there may still be more, still further events, still stranger transformations, unfolding across spans of time so vast that they dwarf all the rest in a future so deep and so dark and so remote that it lies beyond the very edge of comprehension. A future in which the last cold remnants of a long-dead cosmos slowly, imperceptibly, across numbers of years that beggar all imagination, complete their final transformations and settle at last into the ultimate and eternal equilibrium, the true and final heat, death, the end beyond all ends, the last silence, unbroken and unending, stretching on forever in the dark. It is at this point that even physics begins to fall silent, that even our boldest extrapolations reach their limit, that even the language of vast numbers fails us, and we are left simply gazing into a future so deep and so dark that the mind can only turn away, humbled, awed, unable to follow the story any further into the endless night. We have now arrived at the final state, the ultimate destination of the cosmos, the condition toward which everything has been moving from the very beginning. And it has a name that is one of the most evocative and most chilling in all of science. It is called the heat death of the universe. The name is somewhat misleading because the heat death is not hot, but almost perfectly cold, the coldest state the universe can achieve. The heat in the name refers not to warmth, but to a concept from the physics of energy called entropy. And to understand the heat death, and indeed to understand why the universe has an ending at all, we need to understand entropy, because entropy is, in the deepest sense, the reason that time flows, the reason that things change, the reason that the universe has a history and a direction, and the reason that all of it must eventually come to an end. Entropy is often described as a measure of disorder, but a more precise way to think about it is as a measure of how energy is distributed, how spread out and evened out it is. Energy that is concentrated, gathered in one place, available to do work, to power processes, to make things happen, is low in entropy. Energy that is spread out, dispersed, evened out, no longer available to do useful work, is high in entropy. And there is a law of physics, one of the most fundamental and inviolable laws we know, the second law of thermodynamics, which states that in any closed system, entropy always increases over time. That energy always tends to spread out and even out. That concentrations of energy always tend to disperse, never to spontaneously gather. Think of a hot cup of coffee left in a cool room. The heat energy concentrated in the coffee spreads out into the room, warming the air slightly and cooling the coffee until the coffee in the room reach the same temperature and no more heat flows. The energy has spread out, entropy has increased. And crucially, this process only ever runs in one direction. A cup of coffee at room temperature never spontaneously gathers heat from the room and grows hot again. The spreading out of energy is a one-way street, and that one-way street is, in a very deep sense, the arrow of time itself. The reason that the past is different from the future, the reason that things happen, the reason that time seems to flow. Now consider the universe as a whole. In the beginning, in the aftermath of the Big Bang, the universe was in a state of relatively low entropy, with energy concentrated and available, with the potential for structure and process and change. And ever since, the universe has been doing what the second law demands, spreading its energy out, increasing its entropy, moving from concentration toward dispersal. Stars form because gravity gathers gas into dense hot cores, and stars shine because they release concentrated nuclear energy, spreading it out as light and heat into the cold of space. Every process that has ever happened, every star that has ever shone, every living thing that has ever grown and moved in thought, has been part of this great cosmic tendency, this relentless spreading out of energy, this steady increase of entropy. And the heat death is simply the end state of this process, the condition the universe reaches when entropy has increased as far as it can go. When all the energy has spread out and evened out as much as it possibly can, when there are no more concentrations of energy left to disperse, no more differences in temperature, no more gradients, no more potential to do work or drive processes or make anything happen. At the heat death, the universe has reached a state of maximum entropy, perfect thermal equilibrium, a uniform, featureless, ever-expanding thin gas of particles and radiation at a temperature approaching absolute zero. The same everywhere, with no differences, no structures, no concentrations, nothing. And here is the truly profound and truly final thing about the heat death. When the universe reaches maximum entropy, when everything has evened out completely, then nothing can ever happen again. Because every process, every event, every change of any kind requires a difference, a gradient, a concentration of energy that can flow and spread and do work. Life requires it. Thought requires it. Motion, chemistry, physics of any interesting kind, all of it requires differences in energy, and at maximum entropy there are no differences left. The universe becomes a place where nothing changes, where nothing moves in any meaningful sense, where no event can occur, where time itself, though it may technically continue, becomes meaningless because time is measured by change, and there is no more change. This is the heat death, the ultimate fate of the cosmos. Not fire, not collapse, not a dramatic cataclysm, but a slow, quiet, inexorable fading into uniformity. A spreading out of everything into a thin, cold, featureless sameness that endures, unchanging, forever. It is sometimes called the Big Freeze, or the Big Chill, and it is, according to our best current understanding, where everything is headed, the destination written into the physics of energy and entropy from the very beginning. And the timescale, the span over which the universe fades into this final darkness, is beyond all comprehension. By the time the last black holes have evaporated, 10 to the 100th years or more will have passed. And after that, in the truly final era, the era cosmologists sometimes call the dark era, the universe simply continues to expand and cool and thin out forever. The last stray particles drifting ever farther apart in an ever-growing void. The temperature creeping ever closer to absolute zero. The whole thing settling into a stillness and an emptiness, and a silence that has no end, that endures not for billions or trillions of years, but for eternity, for a span of time without limit, a darkness that will never lift, a quiet that will never break, a cold that will never warm. Now, everything I have described so far, the long fading of the stars, the decay of matter, the evaporation of the black holes, the slow settling into heat death, all of it rests on the assumption that dark energy behaves in a particular way, that it remains constant, a steady pressure woven into the fabric of space, driving a steady acceleration of the expansion. This is our best current understanding, the scenario most consistent with the observations we have. But dark energy is a mystery, perhaps the deepest mystery in all of physics, and we do not actually know what it is or how it will behave over the immense spans of time to come. And if dark energy behaves differently than we assume, then the end of the universe could be very different. And some of the alternative endings are even stranger and more dramatic than the slow heat death. Consider first the possibility that dark energy is not constant, but grows stronger over time, that its repulsive push increases as the universe ages. If this is the case, then the universe faces not a slow heat death, but a violent and relatively rapid ending, one called the Big Rip. In the Big Rip scenario, the accelerating expansion grows stronger and stronger, faster and faster, until it begins to overwhelm not just the forces holding distant galaxies apart, but the forces holding everything together at every scale. First, the galaxy clusters would be torn apart. Then individual galaxies ripped to pieces as the expansion overwhelmed the gravity binding their stars. Then, as the expansion grew even more violent, solar systems would be torn apart, planets ripped from their stars. Then the planets and stars themselves would be pulled apart, disrupted by an expansion now so powerful that it overwhelmed even the gravity holding a world or a sun together. And finally, in the last fraction of a second before the end, The expansion would grow so overwhelming that it would tear apart atoms themselves and then the very nuclei of atoms, and then the fundamental fabric of space-time, until everything, every structure at every scale, was ripped to shreds in a final cataclysm, and the universe ended not in a slow fade, but in a violent tearing apart of everything that exists, all the way down to the smallest scales. In a big rip that would consume the cosmos in a matter of a comparatively brief span, rather than the endless slow fate of the heat death. Whether the big rip will happen depends on the true nature of dark energy, on whether its strength is constant or increasing, and this is something we are actively trying to measure. Though the answer remains uncertain, and the big rip, if it comes at all, lies at minimum many billions of years in the future. Then there is the possibility we touched on earlier, the big crunch, in which the expansion eventually reverses and the universe collapses back in on itself. Our current observations suggest this is unlikely because the expansion is accelerating rather than slowing. But if dark energy were to weaken or reverse in the far future, if its repulsive push were somehow to become an attractive pull, then the expansion could halt and reverse, and the galaxies could come rushing back together, and the universe could collapse into a final hot dense state, a big crunch that would mirror the Big Bang that began everything. And some have speculated that such a crunch might not be a true ending, but a transition, that the collapse might trigger a bounce, a new expansion, a new Big Bang, so that the universe might be cyclic, endlessly expanding and collapsing and expanding again, dying and being reborn in an eternal rhythm. These cyclic models are speculative and not favored by current evidence, but they remain among the possibilities that serious physicists explore, and they offer a kind of hope, a vision in which the end is not truly final but is instead the seed of a new beginning. And then there is perhaps the strangest and most unsettling possible ending of all, one that could, in principle, happen at any moment without warning, tonight, or a billion years from now, and which is rooted in the deep physics of the vacuum itself. It is called vacuum decay, and to understand it we need to grasp a subtle idea about the nature of empty space. The vacuum of space, according to modern physics, is not simply nothing. It is a state, a configuration of the fundamental fields that fill the universe, and it has an energy associated with it. And it is possible, according to some of our theories, that the vacuum we live in is not the lowest possible energy state, not the most stable configuration, but a metastable state, a false vacuum, a configuration that appears stable, but is actually poised, like a ball resting in a shallow dip on a hillside, capable of rolling down to a lower state if given the right push. If this is the case, if our vacuum is false rather than truly stable, then it is possible for a tiny region of space to spontaneously transition to the lower energy state, the true vacuum. And once that transition happens in even a single point, it would spread outward at the speed of light, a bubble of true vacuum expanding through the cosmos. And within that bubble, the fundamental constants of physics would be different. The laws that govern matter and energy would be altered. And everything the bubble touched, every atom, every star, every world, would be destroyed, remade according to new and different rules in which the structures we know could not exist. Such a bubble, expanding at the speed of light, would give no warning because it would arrive at the same instant as any light announcing its approach, and it would sweep through the universe silently, invisibly, obliterating everything in its path, ending the cosmos not with a slow fade or a violent rip or a crushing collapse, but with a sudden, total, and irreversible transformation into something in which nothing we recognize could survive. It is important to say that we have no evidence that vacuum decay is imminent, or even that our vacuum is truly false. And if it does happen, the overwhelming likelihood is that it lies unimaginably far in the future. But it remains as a theoretical possibility, one of the strangest ways the universe might end. A reminder that the very ground of reality, the vacuum of space itself, may be less stable and less permanent than it appears. I want to pause now and try to do something that is, strictly speaking, impossible, which is to give you a genuine feel for the timescales we have been discussing. Because I have been throwing around numbers like 10 to the 100th years, and your mind, quite reasonably, has been unable to hold them because the human mind did not evolve to comprehend spans of time like these. and no one's mind can truly grasp them. But we can at least build a ladder of comparisons that carries us, rung by rung, toward an appreciation of how staggeringly vast the future of the universe is, and how brief, by comparison, is everything that has happened so far. Let us start with something graspable. The universe is 13.8 billion years old. A human lifetime is, let us say, 80 years. The age of the universe is roughly 170 million human lifetimes, one after another, back to back. That is already a number too large to truly feel, but you can at least gesture at it. Now, the stelliferous era, the age of stars, will last around 100 trillion years. That is more than 7,000 times longer than the entire current age of the universe. So if the whole history of the cosmos up to this moment, all 13.8 billion years of it, were compressed into a single day, then the age of stars would last more than 7,000 days, about 20 years. We are, on this scale, living in the first few seconds of a 20-year-long day, and the sun and all the stars we can see will be long dead before even the first hour of that day has passed. But this is only the beginning. After the age of stars comes the Degenerate era, with its cooling corpses and its slowly decaying matter, and it lasts, depending on the rate of proton decay, something like 10 to the 40th years. Now, 10 to the 40th years, compared to the 100 trillion years of the age of stars, is a number so much larger that the comparison itself breaks down. If the entire age of stars, all 100 trillion years of it, were compressed into a single second, then the Degenerate era would last, on that same scale, for a span of time vastly longer than the current age of the universe, longer than the age of stars itself, again and again and again. The Degenerate era does not merely dwarf the age of stars. It obliterates it, reduces it to an infinitesimal flicker at the very beginning of a span so much longer that no ratio, no comparison, no analogy can bridge the gap. And then, after the Degenerate era, comes the black hole era, lasting until the last supermassive black holes evaporate, around 10 to the 100th years. And here language and imagination fail completely, because 10 to the 100th years is so much longer than 10 to the 40th years, that the earlier era, vast beyond all comprehension as it was, becomes itself an infinitesimal flicker, a vanishing instant at the dawn of a span so much greater that the mind simply cannot follow. 10 to the 100th is a 1 followed by 100 zeros. To write out the number of years in the black hole era, you would write a 1 and then 100 zeros after it, and each of those zeros represents a factor of 10, a tenfold increase so that the full number is unimaginably, incomprehensibly larger than anything in ordinary human experience or even ordinary human mathematics. And even the black hole era ends. After the last black hole evaporates, the universe enters the dark era, which does not last for 10 to the 100th years, or 10 to the 1,000th years, or 10 to the millionth years. It lasts forever. It has no end. The darkness and the cold and the silence and the emptiness of the final state simply continue, without limit, without end, for a span of time that is not large but infinite. A future without boundaries stretching on and on and on for all eternity. And here is a thought I want to leave you with, before we turn to the strangest possibilities of all. Everything you have ever known, everything that has ever happened in the entire history of the universe up to this moment, all the stars that have shone, all the worlds that have formed, all the life that has arisen, all the civilizations that may exist across the cosmos, all of it, every bit of it, is happening in the first tiny fraction of the first tiny sliver of the very beginning of the universe's existence. We are not living in the middle of cosmic history. We are living in its opening instant, its first bright flash, the briefest and most brilliant moment at the very start of an almost infinitely long story that is overwhelmingly composed of darkness and cold and silence. The age of stars, which seems to us to be simply what the universe is, the natural and permanent condition of the cosmos, is in fact a fleeting golden dawn. A brief window of light and warmth and possibility at the very beginning, before the long, long night that makes up almost the entire future of everything. We are the children of the cosmic morning, alive in the brief hour when the universe is still young and warm and full of light. And that, when you truly absorb it, is not a cause for despair, but a source of wonder, and even of a strange kind of gratitude. Because of all the eras of the universe, of all the vast reaches of cosmic time, we happen to be alive in the one brief age when there are stars in the sky, when the universe is still lit, when there is warmth and structure and the possibility of life. And that is a piece of cosmic good fortune, so extraordinary that it almost defies belief. Let me try one more way of grasping these timescales, because I think it may be the most illuminating of all. A way of compressing the entire lifespan of the universe from beginning to end into a single graspable frame, so that we can see at a glance just how strange our position in cosmic time really is. Imagine the entire history of the universe, from the Big Bang to the final evaporation of the last black hole, compressed into a single calendar year, running from midnight on January the 1st to midnight on December the 31st. On this scale, where the whole vast lifespan of the cosmos is squeezed into 12 months, when do the events we have discussed occur? The answer is startling, and it reveals just how extraordinary our own moment is. On this cosmic calendar, in which the entire history of the universe is a single year, the Big Bang happens at midnight on January the 1st, and the age of stars, the brilliant era in which we live, is over almost before the year has properly begun. In fact, if we scale the calendar so that the final evaporation of the last black hole falls on December the 31st, then the entire age of stars, all 100 trillion years of it, occupies only the very first tiny fraction of the first second of the first minute of January the 1st. The stars, in other words, all of them, from the first to burn to the last to fade, exist and die within the opening instant of the cosmic year. And everything after, all the rest of the year, all the months from January through December, is darkness. The long ages of stellar corpses and decaying matter in evaporating black holes. The vast dark reaches of the deep future that make up virtually the entire lifespan of the cosmos. And where are we on this calendar, we who feel that we live in the ordinary and permanent condition of the universe? We are not just in the first month or the first day or the first hour. We are in the first fraction of the first instant of the very first moment of the cosmic year, so close to the Big Bang, on this scale, that the interval between the beginning of the universe and our own existence is utterly imperceptible. A vanishing sliver at the very start of the year, before the first second has finished ticking. We are the very earliest risers, awake in the first instant of the cosmic dawn, and virtually the entire history of the universe. Virtually all of cosmic time lies ahead of us in the long dark ages we will never see. This is perhaps the single most important thing to understand about our place in cosmic time, that we are not typical inhabitants of a middle-aged universe, but pioneers in a universe so young that it has barely begun, that the era of stars we take for granted is a fleeting opening flash, that the overwhelming majority of the universe's existence is the dark and cold and empty future that follows the death of the stars. We think of the starlit cosmos as the normal state of things, the way the universe simply is. But it is not. It is a brief and special and fleeting condition, the rarest and most precious phase of the entire cosmic story. And we happen, by the most extraordinary luck, to be alive during it, to have arrived in the first instant of the cosmic year, when the stars still shine and the universe is still young and warm and full of light. And on this same calendar, the death of our own sun, 5 billion years in the future, still falls within that same opening instant of January the 1st, so close to the beginning, on the scale of the whole cosmic lifespan, that it too is imperceptibly early, a fraction of the opening moment. Everything that will ever happen to our world, our star, our galaxy, all of it unfolds in the first instant of the cosmic year, and then we and everything we know are gone. And the long, dark remainder of the year stretches out ahead, month after month after month of deepening darkness, the vast and lonely future in which the universe spends almost the entirety of its existence. To hold this image in your mind, the whole lifespan of the cosmos as a single year, and to locate yourself in the first fraction of the first instant of it, is to feel, as vividly as it is possible to feel, both the extraordinary brevity of our moment and the extraordinary privilege of it. The way we have arrived at the very dawn of everything, in time to see the stars, in time to witness the universe at its brief and brilliant best, before the long night that is almost the whole of cosmic time descends and never lifts again. Let us turn now to a question that is, in a way, the most human question we can ask about the end of the universe, which is what becomes of life, of intelligence, of consciousness, in the face of this long dying. Is there anything that life can do? Any way that a sufficiently advanced civilization might resist, or delay, or endure through the fading of the cosmos? Or is the heat death an absolute and inescapable doom for all thinking things, everywhere forever? This is not idle speculation. Serious physicists have thought carefully about the ultimate fate of intelligence in a dying universe, about whether life and thought could persist in some form into the deep future. And their conclusions are fascinating and range from the bleak to the surprisingly hopeful. The fundamental challenge that life faces in the far future is the same challenge that dooms everything else: the relentless increase of entropy, the spreading out and evening out of energy, the fading of the differences in gradients and concentrations that all processes, including the processes of life and thought, depend upon. To live, to think, to compute, to do anything at all requires energy that can flow from a concentrated source to a dispersed sink, requires a difference in energy that can be exploited to drive a process. And as the universe ages and entropy increases, such differences become rarer and smaller and harder to find, until eventually, at the heat death, they vanish entirely, and no process of any kind, including any process of life or mind, can occur. So in the very long run, at the ultimate heat death, life seems to face an absolute limit, a final impossibility, a point beyond which no thought can occur because there is no energy gradient left to power it. But the far future is very far away, and the heat death in the truest sense lies at the infinite end of time. And there may be a great deal that intelligence can do in the immense span before that final limit is reached. One idea which we have explored in another journey is that advanced civilizations might, rather than burning brightly and briefly in the present, choose to conserve their resources and wait, entering a kind of long dormancy, because computation, the physical process of thought, is more efficient at lower temperatures, and the universe is growing colder as it ages. A civilization that wanted to maximize the total amount of thinking it could ever do might therefore hoard its energy and sleep through the warm early ages of the cosmos, waking only in the far cold future when the same store of energy could power vastly more computation, vastly more thought, vastly more experience. Under this idea, sometimes called as the estivation hypothesis, the great civilizations of the universe might be waiting, dormant, planning to awaken in the deep future and carry out projects of thought and experience on scales we cannot imagine, riding the cooling of the cosmos toward ever greater efficiency, extracting the maximum possible amount of meaning and experience from the finite resources available before the final heat death closes off all possibility. Other thinkers have imagined advanced civilizations harvesting energy from the last available sources in the dying universe, drawing power from the evaporation of black holes, or from the last collisions of stellar remnants, or from the slow decay of matter itself, eking out an existence however attenuated, however slow, however strange, deep into the darkening future, adapting their very forms of thought and existence to the ever more meager energy available, slowing down their processes to match the slowing pace of the cosmos so that a single thought might take 1 billion years, and yet still, in some sense, be a thought, still be an experience, still be a form of life persisting against the dark. There is a beautiful and melancholy vision in this, of intelligence stretched across the deep future, ever slower, ever fainter, ever more frugal, clinging to existence in the cooling dark, each thought a monument of endurance, each moment of experience wrested from a universe that is doing everything it can to fall silent. And whether such persistence could continue forever, or whether it must eventually end at some final limit imposed by the heat death, is a question that physicists genuinely debate, that depends on subtle features of physics we do not yet fully understand, on whether the universe truly reaches a state of absolute maximum entropy, or whether the accelerating expansion changes the rules, on whether there are loopholes in the deep physics that might allow thought to persist in some form without limit. We do not know the answer, but there is something profoundly moving in the very asking of the question, in the idea that life and mind, having arisen in the brief bright dawn of the cosmos, might not simply accept the coming dark, but might struggle against it, might find ways to endure, to persist, to keep the flame of consciousness burning as long as physically possible, deep into a future so distant that the stars themselves are ancient memory. And even if, in the end, the heat death is absolute, even if all thought must eventually cease, there is a dignity in the struggle, in the determination of mind to exist, and to experience and to understand for as long as the universe will allow. In the refusal to go quietly into the encompassing dark, there is a strange and mind-bending idea that arises when we consider the truly infinite stretch of time that follows the heat death, an idea that has genuinely troubled cosmologists, and that reveals just how bizarre eternity really is. Recall that at the heat death, the universe settles into a state of maximum entropy, a thin uniform gas of particles and radiation at very nearly absolute zero, with no structure, no differences, no processes, nothing happening. But this is not quite the whole story because of quantum mechanics, because of the restless flickering of the vacuum that never entirely ceases. Even in the deepest heat death, even in the most perfect equilibrium, tiny random fluctuations still occur. Particles still briefly flicker into existence and vanish. The fields that fill space still jitter and quiver at the smallest scales. These fluctuations are almost always utterly trivial. A particle here, a particle there, nothing of any consequence. But over an infinite span of time, in the time after the heat death is truly infinite, even the most improbable fluctuations will eventually occur, given enough time, because infinity is long enough for anything that is possible, however unlikely, to happen, and to happen again, and to happen an infinite number of times. And here's where it gets strange. In an infinite span of time, random fluctuations in the thin gas of the dead universe could, with unimaginable rarity, spontaneously assemble particles into ordered structures. Most of these would be trivial, but occasionally over spans of time so long they dwarf even 10 to the 100th years. A fluctuation could assemble something complex, something ordered, even something resembling a functioning brain. A conscious mind flickering into existence for a moment out of the random churning of the dead cosmos, complete with memories and thoughts and the illusion of a past, before dissolving back into the featureless gas from which it arose. These hypothetical spontaneously assembled minds are called Boltzmann brains, after the physicist Ludwig Boltzmann, who first grappled with the strange implications of entropy and fluctuations. And they pose a genuine puzzle for cosmology. Because if the universe endures for infinite time in a state where such fluctuations can occur, then over that infinite time, an infinite number of Boltzmann brains would spontaneously form, vastly outnumbering the number of ordinary minds like ours that arise through the normal processes of cosmic evolution and biology. And this leads to a disturbing question. How do you know that you are not a Boltzmann brain, a momentary fluctuation in the dead far future, with false memories of a life and a world that never existed, about to dissolve back into the void? It sounds absurd, and most physicists believe there must be something wrong with the reasoning that leads to it, some feature of the true physics that prevents the universe from producing Boltzmann brains in overwhelming numbers. And the puzzle is taken seriously precisely because it seems to reveal a flaw in our understanding, a place where our theories, extended to infinite time, produce conclusions that seem absurd, and where the absurdity is a signal that we are missing something important about the nature of the universe and its ultimate fate. The Boltzmann brain problem is not really a claim that such minds exist. It is a warning sign, a place where the physics of eternity produces paradox, and it reminds us how little we truly understand about the infinite future, about what happens when time stretches on without limit, about whether the heat death is truly the final and eternal state, or whether something in the deep physics changes the picture in ways we cannot yet foresee. And this connects to a deeper uncertainty that runs through this entire journey, which is that the far future of the universe depends on physics we do not fully understand, on the true nature of dark energy, on whether protons really decay, on what happens at the deepest levels of reality over spans of time we can never observe or test. Everything I have described tonight is our best current understanding, drawn carefully from the physics we know. But the physics we know is incomplete, and the far future is a realm we can never visit, never measure, never confirm. A realm we can only reason our way toward, following our theories into the deep dark and trusting that they hold, while knowing that they may not, that there may be surprises waiting in the deep future that would overturn the whole picture. Endings we have not imagined, or perhaps even a way that the story does not end at all. We are like sailors trying to chart a coastline we can never actually reach, reasoning about the shape of a shore that lies beyond the curve of the world. In our maps of the far future, however carefully drawn, are maps of a territory we can never visit, and must be held with humility, as our best guesses about the ultimate fate of everything, rather than as certain knowledge. Let us bring this vast story home for a moment, down from the abstract eras of cosmic time to something closer, something personal, something that will happen to our own star and our own world. Because long before the last star in the universe dies, long before matter decays or black holes evaporate, our own sun will end. And the story of its death is both a small chapter in the great cosmic narrative and a deeply intimate one, because it is the end of the world that gave us birth. Our sun is right now about 4.5 billion years old, roughly middle-aged for a star of its type, burning steadily, converting hydrogen to helium in its core, pouring out the light and warmth that sustains all life on Earth. It has been doing this for 4.5 billion years, and it will continue for roughly another 5 billion years more, a reassuringly long time by any human measure. But the sun's fuel is finite, and when it begins to run low, the sun will not simply fade quietly away. It will die dramatically, and its death will destroy the Earth, or at least render it utterly uninhabitable, long before the sun itself finally goes dark. As the sun exhausts the hydrogen in its core will contract and heat, and its outer layers will expand enormously, and the sun will swell into a red giant, growing to many times its current size, its surface ballooning outward until it may engulf the innermost planets entirely. Mercury will almost certainly be swallowed. Venus will likely be swallowed, and the Earth may be swallowed too, or may narrowly escape being engulfed only to be scorched into a lifeless cinder, its oceans long since boiled away, its atmosphere stripped, its surface transformed into a hellscape of molten rock beneath a monstrous, swollen sun that fills half the sky. But actually, life on Earth will end long before even this, because the sun grows gradually brighter as it ages, and within about 1 billion years, perhaps sooner, the sun will have brightened enough that the Earth will grow too hot for liquid water to persist on its surface, the oceans will evaporate, and the planet will become uninhabitable. A sterilized world circling a slowly brightening star, its age of life over, long before the dramatic red giant phase even begins. So the Earth has at most something like 1 billion years of habitability remaining, which sounds like an eternity, but is, in the grand scheme, a finite and countable span. And after that, whatever has become of life on Earth, whether it has spread to other worlds or vanished entirely, the planet itself will be rendered lifeless by the slow brightening of the aging sun. And then, after the red giant phase, after perhaps swallowing the inner planets, the sun will shed its outer layers entirely, casting them off into space in a beautiful expanding shell of glowing gas that will drift outward for tens of thousands of years. And at the center of that expanding shell, all that will remain of the sun will be its exposed core, a white dwarf, an Earth-sized cinder of incredibly dense degenerate matter, containing much of the sun's mass compressed into a sphere the size of a small planet, glowing white-hot at first with residual heat, but generating no new energy, destined to do nothing for the rest of eternity, but slowly cool. And that white dwarf, the corpse of our sun, will circle the center of the galaxy, or of whatever the galaxy has become, for billions and then trillions of years, cooling gradually from white to yellow to red to a dull dark ember, until eventually, in the deep reaches of the degenerate era, it becomes a black dwarf, a cold dark cinder, invisible, silent, all that remains of the star that once gave light and warmth and life to a small blue world and everything that ever lived upon it. And if proton decay is real, then even that cold cinder will not last forever, but will slowly, over unimaginable spans of time, evaporate away, its matter unraveling particle by particle, until at last nothing remains of our sun at all. Not even a cold, dark corpse. Nothing but a thin, dispersing haze of particles drifting in the dark. The final and complete erasure of the star that was the center of our world, the source of our light, the anchor of our existence. There is something almost unbearably poignant in following the death of our own sun all the way to its ultimate end, in realizing that the star that feels so permanent, so eternal, so much the fixed and unchanging center of our sky and our lives, is itself mortal, is itself moving toward an ending, will itself one day die and cool and fade, and finally, in the deepest future, cease to exist entirely. And there is a lesson in it about the nature of permanence, about how the things that seem most eternal are, on a long enough timescale, as fleeting as everything else, and about how the light we live by, the warmth we depend on, the star we orbit, is a temporary gift, a brief blessing in the cosmic dawn. Precious precisely because it will not last forever. Imagine, if you can, standing on some world and watching the sky change across the vast eras of cosmic time, watching the universe age and fade through the eyes of a series of hypothetical observers scattered across the deep future, each one seeing a sky profoundly different from the one that came before. Tonight, in our own era, the sky is rich and full. We see thousands of stars with the naked eye, the luminous band of the Milky Way arching overhead, and with telescopes we see billions of galaxies stretching across billions of light years. A cosmos brimming with light and structure, the observable universe laid out in all its glory. This is the sky of the cosmic dawn, the richest sky the universe will ever have, and we are privileged to see it. Now move forward 100 billion years. The accelerating expansion has carried all the distant galaxies beyond the horizon of visibility. An observer at this time looking out into the cosmos would see only their own galaxy, the merged remnant of the Milky Way and Andromeda, and the rest of the local group, a single island of stars surrounded by an apparently infinite and empty blackness. The rest of the universe would be gone, invisible, unreachable, and this observer would have no way of knowing it had ever existed. The sky would be smaller, lonelier, the cosmos seemingly reduced to a single galaxy adrift in an endless void. Move forward further, into the late Stelliferous era, trillions of years from now. The bright stars are long dead. The galaxy is dominated by dim red dwarfs and the accumulating corpses of dead stars. The sky, to any observer, would be dark and red and sparse. The brilliant blue-white stars of our own era long since gone. Only the faint red glow of the longest-lived stars remaining. A dim and dying light in a sky growing ever emptier. Move forward into the Degenerate era, past the death of the last star. Now the sky is truly dark. There are no stars shining anywhere, only the cooling corpses of dead stars. White dwarfs fading to black, neutron stars spinning silently in the dark, and the occasional rare flicker of a chance collision, briefly igniting a momentary flame before it too dies. An observer at this time, if any could exist, would look up into a sky of almost perfect blackness, a darkness broken only by the faintest and rarest of glimmers, a cosmos that has forgotten what it was to shine. Move forward into the black hole era. Now even the stellar corpses are gone, evaporated by proton decay or swallowed by the black holes. The universe consists of scattered black holes, unimaginably far apart, each one radiating its faint hawking glow into a darkness so complete, so total, so absolute, that the word darkness barely captures it. There is no sky to speak of anymore, no structure to observe, nothing but the vast and lonely dark, punctuated at almost inconceivable intervals by the death of a black hole in its final flash. And finally move forward into the dark era after the last black hole has evaporated. Now there is nothing at all. No stars, no galaxies, no black holes, no matter, no structure, only the thin and ever-thinning gas of stray particles and radiation, drifting apart in an ever-expanding void, growing colder and emptier and more silent forever. There is no sky because there is nothing to see and no one to see it and nothing for light to reveal. There is only the dark and the cold and the silence and the endless expansion, stretching on without limit for all eternity. This is the sky's long story, from the rich and brilliant dawn we are privileged to witness, through the fading and the dimming and the darkening, to the final and eternal night. And when you look up tonight at the stars, at the thousands of points of light, at the band of the Milky Way, at the galaxies visible through a telescope, I want you to remember that you are seeing the universe at the peak of its beauty, in the brief, bright morning of its existence, in the one fleeting era when the sky is full of light, and to remember that this is a temporary glory, a passing gift, a sight that will fade and vanish and never come again once the long night has fallen. We are among the first minds in the history of the cosmos, and we have arrived early enough to see the universe while it is still lit. And that is a piece of extraordinary good fortune, a privilege granted to us and denied to all the countless generations of minds that may arise in the darkening future, who will look up and see only emptiness where we see splendor. The rich sky is ours for now, for this brief moment in the cosmic dawn, and we should treasure it and marvel at it, and never take it for granted, because it is one of the rarest and most beautiful things the universe will ever produce. And we happen, by the most extraordinary luck, to be alive to see it. Since dark energy is the single most important factor determining the fate of the universe, and since it is also the deepest mystery in modern physics, it deserves a closer look, because our entire picture of the end depends on understanding what it is and how it behaves. And the honest truth is that we are only at the very beginning of that understanding. When physicists first grappled with the discovery of the accelerating expansion, they reached for an idea that Einstein himself had introduced and then abandoned decades earlier. When Einstein first developed his theory of gravity, general relativity, and applied it to the universe as a whole, he found that his equations predicted a universe that should be either expanding or contracting, not static, and at the time everyone believed the universe was static and eternal. So Einstein added a term to his equations, a cosmological constant, a kind of built-in pressure of empty space, tuned precisely to balance gravity and keep the universe static. When Hubble later discovered that the universe was in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. But the discovery of the accelerating expansion brought the cosmological constant back, because a constant energy density inherent in empty space, a pressure woven into the vacuum itself, is exactly the kind of thing that could drive an accelerating expansion. And the simplest explanation for dark energy is that it is precisely this, a cosmological constant, an intrinsic energy of empty space that remains the same everywhere and for all time. If dark energy is a cosmological constant, then it will never change, never grow, never weaken, and the universe will expand forever at an accelerating rate, heading toward the heat death we have described, with the distant galaxies vanishing one by one beyond the horizon, and the cosmos settling eventually into cold and dark and silence. But here is the great puzzle. When physicists try to calculate what the energy of empty space should be, based on the quantum physics of the vacuum, based on the flickering of virtual particles that fills all of space, they get a number that is wrong, catastrophically, absurdly wrong, larger than the observed value of dark energy, by a factor so enormous that it represents perhaps the worst prediction in the entire history of physics. A mismatch between theory and observation of many orders of magnitude. Something is profoundly wrong with our understanding. Some deep piece of physics is missing. Some cancellation or mechanism we do not comprehend must be at work to reduce the enormous predicted vacuum energy to the tiny value we actually observe, and no one knows what it is. This puzzle, sometimes called the cosmological constant problem, is one of the deepest unsolved problems in all of physics, and it means that even as we use dark energy to predict the fate of the universe, we do not actually understand the very thing our predictions depend on. And there are alternatives to the cosmological constant, other ideas about what dark energy might be. Perhaps it is not a constant at all, but a dynamic field, something that changes over time, sometimes called quintessence. And if dark energy is dynamic rather than constant, then its behavior in the far future could be quite different from what a simple cosmological constant would produce, could grow stronger and lead to a big rip, or weaken and allow the expansion to slow, or behave in some other way entirely, changing the fate of the universe in ways we cannot currently predict. This is why measuring dark energy precisely is one of the great goals of modern cosmology, why enormous telescopes and ambitious surveys are being built and conducted right now, mapping the distribution of galaxies across billions of light years, measuring the expansion history of the universe with ever greater precision, trying to determine whether dark energy is truly constant or whether it changes. Because the answer to that question is, quite literally, the answer to the question of how the universe will end. And in recent years, some of these surveys have produced tantalizing hints, not yet conclusive, that dark energy might not be perfectly constant after all, that it might be weakening slightly over cosmic time. And if these hints hold up, if future measurements confirm that dark energy is dynamic rather than constant, it would transform our understanding of the fate of the cosmos, might even reopen possibilities we had thought closed, might change the entire story of the end. So the picture I have painted tonight, the long fade toward heat death, is our best current understanding, the most likely fate given what we currently know. But it rests on assumptions about dark energy that we are still working to confirm, and the true ending of the universe remains, in important ways, an open question, a mystery we are still striving to solve, a story whose final chapter has not yet been written, or rather, has been written in the deep physics of the cosmos, but has not yet been read by us and may not be for a long time to come. We are still learning how the story ends, still measuring, still calculating, still peering into the deep future as best we can, and that ongoing search, that determination to understand even the ultimate fate of everything, is one of the most remarkable things about our species. This insistence on knowing, on understanding, on following the story of the cosmos all the way to its end, even an end so distant that it lies beyond all possibility of our ever witnessing it. There is a question lurking beneath everything we have discussed tonight, a question so deep and so puzzling that it touches the very foundations of physics and even of our experience of reality. And it is this: why does the universe have an ending at all? Why does it change? Why does it age? Why does it move inexorably from the bright ordered dawn toward the cold disordered dark? The answer, as we have seen, is entropy, the relentless increase of disorder, the spreading out of energy demanded by the second law of thermodynamics. But this only pushes the question deeper, because the second law says that entropy always increases, which means that in the past, entropy was always lower, which means that at the very beginning, at the moment of the Big Bang, entropy must have been extraordinarily, almost impossibly low. The universe began in a state of remarkably low entropy, a state of high order, of concentrated available energy. And it is this low entropy beginning that makes possible everything that has happened since. All the structure, all the stars, all the life, all the change, all the flow of time itself. And this is genuinely mysterious because a low entropy state is, by its very nature, extraordinarily improbable, extraordinarily special, extraordinarily rare among all the possible states the universe could have been in. Why did the universe begin in such a special, such an ordered, such a low entropy state, rather than in the far more probable state of high entropy and disorder? This is one of the deepest questions in all of physics, sometimes called the problem of the arrow of time, or the past hypothesis, and it is not fully answered. We do not know why the universe began in such a special low entropy state, and this unexplained fact, this mysterious low entropy beginning, is the ultimate source of the arrow of time. The reason that time has a direction, the reason that the past is different from the future, the reason that we remember the past but not the future, the reason that things happen, the reason that the universe has a story with a beginning and a middle and an end. Everything we experience as the flow of time, everything we understand as cause and effect, as memory, as change, as the difference between the settled past and the open future, all of it traces back to that mysterious low entropy beginning, to the fact that the universe started in a state of high order and has been increasing in disorder ever since. And the end of the universe, the heat death, is simply the completion of this process, the moment when entropy reaches its maximum, when the order of the beginning has been entirely spent, when the arrow of time reaches its target and can go no further. When the great unwinding that began with the Big Bang finally, after unimaginable spans of time, comes to its end. In a sense, the entire history of the universe, from the Big Bang to the heat death, is a single vast process of entropy increase, a single grand unwinding, a single arrow of time flying from the ordered dawn to the disordered dark. And everything that happens within that history, every star, every galaxy, every world, every living thing, every thought, is a temporary eddy in that great flow, a local and fleeting increase in order made possible only by a larger increase in disorder elsewhere. A brief and beautiful complexity riding on the back of the universe's relentless slide toward equilibrium. Life itself, in this view, is a kind of entropy engine, a process that creates local order, the intricate order of a living cell, of a body, of a brain, of a civilization. By consuming concentrated energy and releasing it as dispersed waste heat, increasing the total entropy of the universe even as it creates islands of local order. You sitting there listening to this are a temporary and exquisite structure of order, maintained by the constant consumption of energy, by the food you eat and the warmth of your sun, and every moment of your existence. Every thought you think, every heartbeat, contributes to the increase of entropy in the universe, moves the cosmos a tiny step closer to its final equilibrium. We are all, in this sense, part of the great unwinding, participants in the flow of time, agents of the entropy increase that will, in the fullness of time, bring about the end of everything. And there is something both humbling and strangely beautiful in this understanding, in realizing that our very existence, our capacity for thought and order and complexity, is possible only because the universe began in a special low entropy state and is spending that order gradually across the eons, and that we are among the beneficiaries of that primordial order, alive in the brief window when enough of it remains to make stars and worlds and minds, before the great unwinding is complete and the universe settles into its final and eternal equilibrium. We are children of the low entropy dawn, temporary structures of exquisite order, riding the arrow of time from the bright beginning toward the dark end, and our existence, brief and improbable and precious, is a fleeting gift of the universe's mysterious and ordered birth. There is a question that naturally arises as we contemplate this universal dissolution, and it is a question about information, about whether anything of what existed is preserved in any form through all the decay and evaporation and fading, or whether everything is simply and utterly lost. When a star dies, when matter decays, when a black hole evaporates, what happens to the information that those things contained, the intricate details of their structure, the arrangement of their particles, the record of what they were? This is not an idle question. In physics, information has a kind of fundamental status, and there is a deep principle rooted in quantum mechanics that suggests information can never truly be destroyed, that the detailed quantum state of any system, however scrambled or transformed, is in principle preserved, that the universe keeps a perfect record of everything, that nothing is ever truly, completely lost. This principle came into dramatic conflict with the physics of black holes, in a puzzle we have explored in another journey, the black hole information paradox, which asks what happens to the information about everything that falls into a black hole when that black hole eventually evaporates through Hawking radiation. For a time it seemed that black holes might destroy information, might violate the deep principle of its conservation, but the emerging understanding, hard-won over decades of theoretical work, is that information is not destroyed even by black holes, that it is somehow encoded subtly and inaccessibly in the radiation that the black hole emits as it evaporates, that the universe keeps its books even through the death of a black hole, that nothing is ever finally erased. And if this is true, then it has a strange and haunting implication for the end of the universe, because it means that in some deeply scrambled and utterly inaccessible form, the information about everything that ever existed, every star, every world, every living thing, every thought, every moment of every life, might be preserved and coated in the thin gas of particles and radiation that fills the dead universe, carried forward through all the decay and evaporation into the final darkness. Never truly lost, even if never again readable, even if scrambled beyond any possibility of recovery. The universe in this view is a perfect archive, a cosmic memory that preserves the record of everything that has ever happened, even as the things themselves pass away. Even as the stars die and the matter decays and the black holes evaporate and the whole cosmos fades into the final dark. Everything that was, in some sense still is, encoded in the deep structure of reality, held forever in the scrambled correlations of the particles left behind. A memory of the universe's brilliant youth carried forward into its endless old age. Whether this preservation of information means anything, whether it constitutes any kind of continuation or immortality, is a matter of interpretation and philosophy rather than physics. And the information, however perfectly preserved, is scrambled so thoroughly, dispersed so completely that it could never be read or recovered or reassembled, so that in any practical sense the things it records are gone, dissolved, ended. And yet there is something in the idea that appeals to a deep human longing, the idea that nothing is ever truly lost, that the universe remembers, that the record of everything that ever was persists in some form forever, even into the final darkness, even when there is no one left to read it. It offers a strange and cold comfort, the comfort of a permanence that is real in the deepest physics, even if it is inaccessible and meaningless in any practical sense. The comfort of knowing that the universe, whatever else it does not simply erase its own history, that the great story it tells from the bright dawn to the dark end is written somewhere in the deep structure of reality and is not lost even when the telling is done. But I do not want to offer false comfort, and the honest truth is that this preservation of information, real as it may be in the deep physics, does not change the fundamental character of the end, which is that everything we know and love and are, every star and world and living thing and thought, will pass away, will dissolve into the final darkness, will cease to exist in any form that matters to us or that could ever again matter to anyone, because there will be no one and nothing that could ever again become someone, and the universe will settle into its eternal and unchanging equilibrium, its perfect archive holding a record that no one will ever read, a memory with no one to remember, in a darkness without end. Not everyone accepts that the story ends in eternal darkness, and some of the most creative minds in cosmology have proposed alternatives, models in which the end is not truly final, in which the death of the universe is followed by a new beginning, in which the cosmos is not a single arc from birth to death, but an endless cycle or a perpetual process of renewal. And while these ideas remain speculative and are not the mainstream view, they are taken seriously by serious scientists, and they offer a different vision of the ultimate fate of everything, one in which the darkness is not the end of the story, but a chapter in an endless book. One such idea comes from the physicist Roger Penrose, who won the Nobel Prize for his work on black holes and general relativity, and it is called conformal cyclic cosmology, and it is one of the most beautiful and strange ideas in all of cosmology. Penrose begins with the far future of the universe we have described, the heat death, the state in which all the matter has decayed and all the black holes have evaporated, and nothing remains but a thin gas of photons and other massless particles drifting in an ever-expanding void. And he makes a profound observation. In such a state, a universe containing only massless particles like photons, there is a sense in which size and time lose their meaning, because massless particles do not experience time and do not have a natural scale of size. And Penrose argues that in this condition, the vast, cold, empty, dying universe becomes, in a deep geometric sense, indistinguishable from the hot, dense, tiny universe of the Big Bang, that the end and the beginning become mathematically equivalent, so that the heat death of one universe can be smoothly reinterpreted as the Big Bang of the next. In this vision, the death of the universe is not an ending, but a transition, a doorway, and the cold, dark, final state of our cosmos becomes the hot, dense initial state of a new cosmos, a new Big Bang, a new universe rising from the ashes of the old. And this process repeats endlessly, each universe which Penrose calls an eon, giving birth to the next in an infinite sequence, an eternal cycle of cosmic death and rebirth, without beginning and without end. It is a breathtaking idea, and Penrose has even claimed to find hints of the previous eon written faintly in the afterglow of our own Big Bang, though these claims remain deeply controversial and unconfirmed. Other cyclic models take different approaches. Some propose that the universe undergoes a big crunch, collapsing back together, and then bouncing into a new expansion. A new Big Bang, in an endless rhythm of collapse and rebirth. Others, drawing on ideas from string theory, imagine our universe as one of many, existing in a higher dimensional space, periodically colliding with a neighboring universe in a collision that triggers a new Big Bang, over and over, forever. What all these cyclic models share is the vision that the end is not truly final, that the universe, or the larger reality of which it is a part, renews itself endlessly, that death gives way to birth, that the cosmos is not a single mortal arc, but an immortal cycle. And this vision offers a kind of hope, a sense that the darkness we have described is not the last word, that beyond the heat death lies not eternal nothingness, but a new dawn, a new universe, a new beginning, and perhaps in that new universe, new stars, new worlds, new life, new minds, looking up at their own sky and asking their own questions, unaware that they are the latest chapter in an endless story. And then there is the idea of the multiverse, the possibility that our universe is not all that exists, but is one of countless universes, perhaps infinitely many, each with its own properties, its own laws, its own history and fate, bubbling into existence and expanding, and perhaps ending in a vast eternal froth of universes beyond our own. If the multiverse is real, then even if our universe ends, even if it fades into eternal darkness, other universes may continue, may flourish, may give rise to their own stars and worlds and life, so that the ending of our cosmos would be not the end of everything, but merely the end of one universe among endless many. A single wave breaking on an infinite shore, while elsewhere, in other universes, in other regions of the vast multiverse, the story of existence continues forever. These ideas, cyclic cosmology and the multiverse, are speculative, uncertain, at the very edge of what science can currently explore. And they may be wrong, may be corrected or overturned by future understanding. But they remind us that the story of the end of the universe is not finished, that our understanding is incomplete, that there may be more to the ultimate fate of everything than the bleak vision of eternal heat death, that the cosmos may hold surprises we cannot yet foresee, doorways beyond the darkness, new beginnings beyond the end. And whether or not any of these ideas prove true, they express something deep in the human spirit, a refusal to accept that the story simply ends, a hope that beyond every ending lies a new beginning, a faith that existence, in some form, somewhere, continues, that the light, though it fades here, is not extinguished everywhere and forever, that the great story of the cosmos, whatever its ultimate shape, is not a tragedy ending in silence, but perhaps an endless epic, renewing itself forever, in eon after eon, universe after universe, world without end. It is worth stepping back and asking how we can possibly claim to know any of this, how a species that has existed for a few 100,000 years, on a single small world, watching the cosmos for a mere few centuries with instruments, can presume to describe the fate of the universe across spans of time so vast that they dwarf the current age of everything by factors beyond comprehension. It is a fair question, and the answer reveals both the extraordinary power and the genuine limits of science. We cannot, of course, observe the far future. We can never travel there, never measure it, never confirm our predictions by watching them come true, because the events we describe lie trillions upon trillions of years ahead, beyond any possibility of observation. So how do we know? We know, or rather we reason, by understanding the fundamental laws of physics, the laws that govern how matter and energy and space and time behave, and by applying those laws carefully and rigorously to the conditions we expect in the far future. The laws of physics, as far as we can tell, are the same everywhere and at all times, the same in the distant past as in the present, and presumably the same in the far future. And if we understand those laws, we can calculate how the universe will evolve, how the stars will die, how the matter will decay, how the black holes will evaporate, how the whole cosmos will fade toward its final state. It is the same physics that lets us predict the return of a comet decades in advance, or calculate the path of a spacecraft across the solar system, or understand how a star shines, extended and applied to the grandest possible scale and the longest possible time scale. And the predictions are only as good as our understanding of the underlying physics, which is why there is genuine uncertainty, why the far future remains, in important ways, an open question. Some of the physics we are confident about. We understand very well how stars form and live and die, and our predictions about the death of the stars and the end of the stelliferous era rest on solid and well-tested science. We understand the expansion of the universe and its acceleration, measured directly through careful observation, though the nature of the dark energy driving it remains mysterious. Other parts of the story rest on physics that is less certain. Proton decay has never been observed, and whether it happens at all, and if so, how quickly, remains genuinely uncertain, which means the details of the decay of matter in the Degenerate era are correspondingly uncertain. Hawking radiation, the evaporation of black holes, is a prediction of theory that has never been directly observed because the radiation from any real black hole is far too faint to detect, though the theoretical case for it is strong. And the deepest questions about the ultimate fate of the universe, about the true nature of dark energy, about what happens at the final heat death and whether it is truly eternal, rest on physics that we do not yet fully understand, that we are still working to comprehend, that may hold surprises we cannot foresee. So the honest position is this: the broad outline of the story we have told tonight, the death of the stars, the fading of the galaxies, the long descent toward darkness and cold, is our best current understanding, well grounded in tested physics, likely to be correct in its general shape. But the details, and especially the details of the deepest future, are uncertain, dependent on physics we are still working to understand, subject to revision as our knowledge grows. The story of the end of the universe is not a settled fact, but a scientific prediction, a reasoned extrapolation from the laws of physics as we currently understand them, held with appropriate humility, open to revision, a best guess about the ultimate fate of everything, rather than a certain and final truth. And there is something remarkable in the very fact that we can make such predictions at all, that a species can reason its way across trillions of years, can follow the story of the cosmos to its distant end, can describe with real confidence the broad shape of a future so remote that no one will ever witness it. It is one of the great achievements of the human mind, this ability to understand the universe not just as it is, but as it will be, to read the future of everything in the laws of physics, to comprehend our own cosmic context across the fullest possible span of time. We are the part of the universe that has learned to understand itself, not just its present, but its past and its future, its origin and its fate. And that understanding, however incomplete, however uncertain, is one of the most extraordinary things that has ever emerged in the history of the cosmos, a small, warm spark of comprehension in the brief, bright dawn, reasoning its way toward an understanding of the endless dark that lies ahead. So what do we do with this knowledge? What does it mean for us, for our brief lives on this small world, to know that everything ends, that the stars will die and the galaxies fade, and the matter decay, and the universe settle at last into an eternal and unchanging darkness? It would be easy to respond with despair, to conclude that if everything ends, then nothing matters, that all our striving and loving and building and dreaming is futile, doomed, ultimately meaningless in a cosmos destined for oblivion. And I understand that response, and I will not pretend it has no force. There is a genuine vertigo in contemplating the end of everything, a genuine grief in knowing that all of this, all the beauty and richness and wonder of the universe, will one day be gone, that even the memory of it will fade, that the final state of the cosmos is a darkness in which nothing we value can exist. But I want to offer a different response, one that I find truer and more honest, and in the end, more consoling, though it is not a cheap or easy consolation. The first thing to say is that the end is unimaginably far away. The death of the sun lies billions of years in the future. The death of the last star lies 100 trillion years ahead. The final darkness lies at spans of time so vast that the entire history of the universe up to now is less than the first instant of the first moment of the dawn. Nothing we do, nothing we value, nothing we love is threatened by the heat death, because the heat death is so remote that it has no bearing whatsoever on our lives, on our world, on our civilization, on anything that could possibly matter to us or to any conceivable descendant of ours for spans of time beyond all reckoning. To let the distant heat death cast a shadow over our present lives is like a person refusing to enjoy a beautiful morning because they know that billions of years hence, the sun will die. The morning is real and beautiful and ours, and the distant death of the sun does not diminish it in the slightest. But there is a deeper point, one that goes beyond the mere remoteness of the end. It is this: the fact that something ends does not make it meaningless. In fact, in a very deep sense, it may be precisely the finitude of things, precisely the fact that they end, that gives them their meaning and their preciousness and their beauty. A piece of music is beautiful, and its beauty is not diminished by the fact that it ends. Indeed, the ending is part of the music, part of its shape and its meaning. And a piece of music that never ended, that simply went on forever, would not be more beautiful but less, would cease to be music at all and become mere endless noise. A human life is precious, and its preciousness is bound up with its finitude, with the fact that our time is limited, that we will not live forever, that each moment is fleeting and unrepeatable, and therefore infinitely valuable. It is the ending that gives the story its shape, the finitude that gives the moment its weight, the transience that gives existence its poignancy and its beauty. And the same may be true of the universe itself. The cosmos is beautiful, gloriously, achingly beautiful, in its brief bright dawn, in this fleeting era of stars and galaxies and life. And its beauty is not diminished but perhaps deepened by the knowledge that it will not last forever, that this is a passing splendor, a temporary glory, a brief and precious moment of light between the dark before the beginning and the dark after the end. We are alive in the morning of the universe, in the one brief age when there are stars in the sky and warmth in the void and the possibility of life and thought and love, and the fact that this age will end, that it is fleeting and finite and will not come again, does not make it meaningless, but makes it precious beyond all measure. A gift so rare and so beautiful that we should be overwhelmed with gratitude simply to be here, simply to witness it, simply to be alive at all in a cosmos that is, for the most part, and for almost all of its vast history, dark and cold and empty and silent. We are the lucky ones, the ones who arrived in time to see the stars, and the transience of that gift is not its tragedy, but its glory. There is another thought I want to offer, one that I find genuinely astonishing when I truly absorb it, and it concerns what we are and what our existence means in the context of this vast cosmic story. Consider the universe as we have described it, this enormous and ancient and mostly empty cosmos, evolving across unimaginable spans of time, from the bright dawn to the dark end. For almost all of that story, across almost all of that space and time, there is no one to see it, no one to understand it, no one to know that it exists at all. The stars shine and the galaxies turn, and the black holes evaporate in a cosmos that, for the most part, is utterly without witness, without awareness, without any mind to comprehend the grandeur and the tragedy of the whole vast unfolding. And yet here, on this small world, in this brief moment of the cosmic dawn, something extraordinary has happened. The universe has produced, through the long, slow working of physics and chemistry and biology and evolution, a part of itself that can look back at the whole, that can understand it, that can comprehend its origin and its structure and its fate, that can feel wonder at its beauty and grief at its ending, and gratitude for the brief privilege of existence. We are that part. We are the universe become aware of itself. We are the cosmos grown conscious, the matter of the universe organized after 13 billion years, into a form that can look up at the stars and understand what they are, that can reason its way back to the Big Bang and forward to the heat death, that can hold the entire vast story of existence in a single comprehending mind. When you look up at the night sky and feel wonder, that wonder is the universe feeling wonder at itself. When you understand the death of the stars, that understanding is the cosmos understanding its own fate. When you grieve for the beauty that will pass, that grief is the universe mourning its own transience. We are not separate from the cosmos, not outside observers of an alien universe. We are made of the same matter as the stars, the very atoms of our bodies forged in stellar cores and scattered by stellar deaths. And we are the universe's own way of knowing itself, its own consciousness, its own comprehension, arisen briefly in the cosmic dawn to witness and understand and marvel at the whole vast unfolding of existence before the long night falls. And this, I think, gives our existence a significance that the coming darkness cannot touch. For a brief moment in the vast history of the cosmos, the universe woke up. It became aware of itself. It understood its own story. And that awakening, that comprehension, that brief flowering of consciousness in the dawn of everything, is one of the most extraordinary things that has ever happened or will ever happen in the entire history of the universe. A thing so rare and so precious that it may have happened only here, on this one small world, in this one brief moment. Out of all the vastness of space and all the eons of time, we are the witnesses. We are the ones who see. And whether or not our kind of consciousness ever arises again, whether or not there are other minds elsewhere in the cosmos or in the deep future, the fact that the universe became aware of itself at all, even once, even briefly, even here, is a triumph beyond all measure. A victory of comprehension over the vast, unknowing dark, a moment of light and understanding in a cosmos that is, for almost all of its existence, without witness and without awareness. And so when we contemplate the end of the universe, the long fade toward darkness and cold and silence, we should not only feel grief, though grief is appropriate, we should also feel a fierce and profound pride and gratitude and wonder that we were here, that we existed, that the universe through us came to know itself, came to understand its own story, came to witness its own beauty in the brief, bright morning before the endless night. That is our role in the cosmic story, our part in the great drama of existence, to be the eyes through which the universe sees itself, the mind through which it understands itself, the heart through which it feels the wonder and the grief of its own fleeting and precious and beautiful existence. And that is a role worth playing, a privilege worth cherishing, a gift worth all the gratitude we can muster, regardless of how the story ends. Because the ending does not erase the fact that, for a brief and shining moment, the universe woke up and looked around and understood and marveled at the beauty of it all. There is one more idea I want to share before we close, a way of seeing our place in this story that I find genuinely transformative. And it has to do with the relationship between life and the great cosmic tendency toward disorder. We have said that the universe is running down, that entropy always increases, that everything is spreading out and evening out toward the final equilibrium of heat death. And in the face of this, life can seem like a doomed anomaly, a temporary and futile pocket of order swimming against an irresistible tide. But there is another way to see it, a way that reveals life not as a contradiction of the cosmic order, but as one of its most remarkable expressions. Life does not violate the second law of thermodynamics. It could not, because nothing can. Instead, life is a way that the universe increases its total entropy more efficiently, a kind of accelerant for the very process of running down. A living thing maintains its own internal order, its exquisite and improbable structure, by consuming concentrated energy, by taking in order rich food or sunlight and releasing disordered waste heat. And in doing so, it increases the total entropy of the universe faster than would happen if it were not there. Life, in other words, is one of the ways the universe spends its precious store of order, a channel through which the great unwinding flows, and paradoxically, the local order of a living thing, its structure and complexity and beauty, is created precisely by accelerating the global increase of disorder. This means that we, and all living things, are not opponents of the cosmic tendency, but its agents. Not exceptions to the flow of time, but expressions of it, riding the arrow of entropy from the ordered dawn toward the disordered dark, and creating in the process islands of astonishing order and complexity and beauty, minds and civilizations, and works of art and moments of love and understanding, temporary and fleeting but real, wrested from the raw material of the universe's slow decline. And there is something profoundly beautiful in this, in realizing that the very complexity and richness and beauty of life, of consciousness, of everything we value, is made possible by, is a part of, is an expression of, the same great cosmic process that will eventually bring about the end of everything. The universe is running down, and we are part of how it runs down, and yet in that running down, in that spending of the primordial order, the universe produces us, produces beauty, produces love, produces minds that can understand and appreciate and marvel at the whole vast process. And that is not a tragedy, but a wonder. Not a contradiction, but a kind of cosmic poetry. The universe creating beauty and consciousness and meaning in the very act of its own dissolution. Lighting brief and brilliant fires of order and complexity as it spends its way toward the final dark. We are the universe's way of burning beautifully as it dies, of creating meaning and beauty and understanding in the brief window between the ordered beginning and the disordered end, of wringing every possible drop of wonder and complexity and consciousness from the finite store of order that the cosmos was born with. And that, I think, is a role worth celebrating, a part worth playing with all the passion and gratitude and wonder we can bring to it. Because we are here now, in the brief bright window when it is possible, alive and conscious and capable of love and understanding, burning beautifully in the cosmic dawn, and the fact that the fire will eventually go out does not diminish the beauty of the burning, but makes it all the more precious, all the more worthy of our wonder and our gratitude and our fierce and joyful celebration of the extraordinary privilege of being alive at all. Think for a moment about what it took for you to be here, listening to this in this precise sliver of cosmic time. The universe had to begin in exactly the right way, with exactly the right amount of order, exactly the right laws, exactly the right balance of forces for stars to form and shine and forge the elements. Generations of stars had to live and die to build the carbon and oxygen and iron of which you are made, scattering those elements across space so that they could gather into a new star and its planets. A particular star, our sun, had to form in a quiet corner of a spiral galaxy, and a particular world had to condense at just the right distance from it, with just the right conditions for water and chemistry and life. And then, across 4 billion years, life had to arise and survive and evolve through countless improbable steps and narrow escapes, from the first self-replicating molecule to the first complex cell, to the first animal, to the first creature that could wonder, until at last, in the brief bright morning of the universe, a mind emerged that could look up at the stars and understand what they are and where they came from and how they will end. Every step of that chain was improbable, and the whole chain together is so improbable that it defies all reckoning. And yet here you are, the end product of 13 billion years of cosmic evolution, a conscious mind alive in the first instant of the cosmic dawn, capable of holding the entire story of the universe from its beginning to its end in a single act of understanding. That is not nothing. That is very nearly everything. That is the universe achieving in you the most extraordinary thing it has ever achieved, an awareness of itself, a comprehension of its own vast and beautiful and tragic story, and it is happening now, in you, in this moment, in the fleeting and precious dawn before the long night falls. And so the great clock of the cosmos ticks on, indifferent and magnificent, carrying us and everything we know from the bright beginning toward the distant end, and in the brief span granted to us in this fleeting and luminous morning of all things, we have been given the chance to see, to understand, to marvel, and to love. And that chance, however brief, is the most precious gift the universe has ever offered, and it is offered right now to you. Hold that thought as we part, and carry it with you out into the ordinary business of your life, into your morning and your work and your evening. The knowledge that you are a brief and brilliant flame of consciousness burning in the dawn of a universe that is almost all still ahead of it, and that this, all of this, the stars and the sky and your own beating heart, is a wonder beyond all deserving, and yours for now to witness. So let us gather the whole story together, one last time, and hold it in our minds as a single vast arc from the beginning to the end. The universe began 13.8 billion years ago in a state of extraordinary order and heat and density, and it has been expanding and cooling and increasing in entropy ever since. It passed through a brief and brilliant dawn, the age of stars in which we now live, a fleeting golden era of light and warmth and structure and life, which will last 100 trillion years, and which we have caught in its first bright moment. The stars will die, first the bright, massive ones, then the sun-like ones, then at last the long-lived red dwarfs, until the final star burns out and the age of light ends. The galaxies will fade and, one by one, recede beyond the horizon of visibility, carried away by the accelerating expansion, until any observer is left alone with a single island of stars in an apparently infinite void. The stellar corpses will cool, and if proton decay is real, slowly evaporate, until all ordinary matter has dissolved into a thin cold haze. The galaxies will dissolve, their remnants scattered or swallowed by the black holes at their centers. And then, in the longest era of all, the black holes themselves will slowly evaporate through Hawking radiation, over spans of time so vast they defy all comprehension, until the last and largest black hole radiates away its final mass in a last brief flash, and with it goes the last structure, the last concentration of energy, the last object in the universe. And then in the final era, the dark era, the universe simply continues, expanding and cooling and thinning forever, settling into the heat death, the state of maximum entropy, a thin uniform cold gas of stray particles drifting apart in an ever-growing void. A darkness and a silence and an emptiness that endures, unchanging for all eternity, because nothing can happen anymore, because all the differences have evened out, because the great unwinding that began with the Big Bang has finally, after unimaginable spans of time, reached its end. That is the story of the end of the universe as best we understand it. A story of slow fading, of gradual darkening, of the long descent from the bright ordered dawn to the cold disordered dark. And yet woven through that story of ending, there are threads of a different kind, uncertainties that leave the door open, dark energy whose true nature we do not know, cyclic models in which the end gives way to a new beginning, the possibility of a multiverse in which other universes flourish even as ours fades, the deep principle that information is never truly destroyed, the persistence of intelligence struggling against the dark, and above all, the extraordinary fact that, for a brief moment in the cosmic dawn, the universe woke up and came to know itself. Through us, through minds like yours and mine, alive in the one fleeting era when there are stars in the sky. And so I come back at the end to where we began, to you listening to this, wherever you are, whatever hour it is, alive in the brief, bright morning of the universe. The stars are still shining tonight. The galaxies still fill the sky. The sun will rise tomorrow and warm your world and sustain your life, as it has for billions of years and will for billions more. The universe is still young, still lit, still full of beauty and wonder and possibility, and you are here, alive, conscious, able to look up and understand and marvel at it all in the one brief era when all of this is possible. The end is unimaginably far away, and it does not diminish the beauty and the preciousness of this moment, this life, this world, this universe in its glorious dawn. If anything, it deepens it, makes it more precious, more urgent, more worthy of our wonder and our gratitude and our love. So look up tonight if you can at the stars and know that you are seeing the universe at the peak of its beauty, in the brief, bright morning of its existence, a sight so rare and so precious and so fleeting that you should treasure every moment of it, and know that you are the universe become aware of itself, the cosmos grown conscious, the eyes through which existence sees its own beauty, and that this, whatever comes after, whatever darkness lies ahead, is a privilege and a wonder beyond all measure. If this journey moved you, if it made the sky look different, deeper, more precious, then do the 3 small things that help these journeys reach other minds like yours. Subscribe so you are here for the next one. Like the video so the platform carries it further into the dark. And in the comments, along with the city and the hour you are watching from, tell me how it makes you feel. This knowledge that everything ends, whether it fills you with grief or wonder or gratitude or peace. Because I read every single one. And the conversation down there, minds reaching out to other minds across the dark, refusing to be silent, is itself one of the most beautiful things the brief, bright dawn of the universe has produced. The stars are still up there, still shining, still ours for now, in this fleeting and precious morning of the cosmos. Treasure it while it is yours in the brief, bright morning of everything. And sleep well.